random access memory could be categorized into two main categories in the classes: the static RAMs and dynamic RAMs. In the case of static RAM, the information is stored in latches, so they remain there, and there's as long as there's power provided, for the latches. While on the other hand, for the dynamic RAMs, the information is stored in the form of electrical charges on capacitors. And since it is done in this way, and since the charge could leak over time, a periodic refresh of charge is required in order to make sure that the data is stored properly in the RAM. So we have static RAM and the dynamic RAM, and we'll go to details into them later. We can also classify the RAM memories into the volatile and non-volatile classes. In the case of volatile RAMs, the information stored in the memory will be lost once the power is turned off, and if we have the non-volatile RAM, the information will be kept there even if we lose the power. So the non-volatile RAM will keep the information even if the power is turned off. You can think of the hard disk of the computer, to get an idea. Even if you turn off the computer, the information that you had in the memory of the system will be still there, and next time that you turn the system on, you will have access to that information. So in some sense, you can have an understanding of the non-volatile memory. Over here, we can see how the single cell of a static RAM looks like. So we are talking about the static RAM. Therefore, over here, the storage element is not a capacitor, but it is a latch. We are using an SR latch over here, and you can see the single memory element of the static RAM. At the heart, we have the SR latch. So this is the main element of our memory cell. But then together with that, we are using also 4 AND gates with 2 inputs. 2 AND gates are used on the input side. They receive one input. Both of those in the 2 AND gates receive one select input, as you can see here. So if we have select equal to 0, if select is equal to 0, one input to those ANDs will be equal to 0, and therefore their outputs will be also equal to 0. And as a result, the SR latch will not change its content. On the other hand, this select input is also connected to the input of the other 2 AND gates that we have on the output side. So you can see over here that if select is equal to 0, one input to those AND gates will be also equal to 0, and then the C and not C outputs that we have on the output side will be also equal to 0. This is important when we want to combine multiple number of RAM cells together, because in that case we will OR the outputs of the cells with each other. Therefore, when a given cell is not selected, it will give us 0, and then if we OR it with the others, it will be fine. On the input side, when the select is equal to 0, whatever value we have for the B and not B will not be important. But when the select is equal to 1, then the data that we receive from B and not B, if we set the select to 1, let me just change it here. If we set select to 1, this 1 will appear at one input of the AND gates. Then we will have B and not B here, and therefore the input to the S and R will be B and not B. Then depending on the value that we have for B and not B, the information stored in the cell could be changed. We can set it or we can reset it. Alright, so that's what we have for a single cell. Now we can see over here what is called as the static RAM bit slice. So basically we are combining multiple number of the RAM cells, static RAM cells with each other. In this example, we have 2 to the power of n number of the cells. So cell number, we can call them cell number 0, cell number 1, down to cell number 2 to the power of n minus 1. You can see that the cells are identical. So the cell that we have here is identical in terms of its structure to the cell that we have here. All of them are basically the same. We just put multiple number of them one after the other one. In terms of the control inputs, how to write the data into and how to read the data from the memory, from the RAM bit slice, we need to introduce some additional piece of circuitry that you can see over here and there. And now I will explain how they are working. But regardless of that, if we want to select a given location in this RAM bit slice, we need to provide the information through the word select input. The word select input is the signal that we pass to the select input of each cell in it. So with the word select, which is somehow the memory address, the select input to one of the cells will be equal to 1, and for the rest it will be equal to 0 at any time instance. Then over here we can see how the reading or writing of the data is performed. The bit select is similar to the chip select. Indeed, it is, if it's set to 1, it means that this piece of memory is selected. If it's set to 0, it means that this piece of memory is not selected. And we can see it over here as well. If let's follow it. If bit select is set to 0, we will have 0 here. The output of this AND will be 0. The input to these ANDs will be 0, and therefore the output from these AND gates will be 0. And then we can see that B and not B inputs to the AND gates will be equal to 0, and therefore output from these AND gates will be also equal to 0, and as a result the content of the memory will not change. It will remain the same. On the output side, you can see that if bit select is equal to 0, the input to this AND gate will be equal to 0, and then its output will be also equal to 0, regardless of whatever we had inside the memory. But on the other hand, if we set bit select to 1, let me just clean these things that I already have written. If we set bit select equal to 1, it means that this part of the memory is selected. Then 1 will appear here, and then it, depending on whether we have read or writing, we can read from the memory or we can write into the memory. Let us consider them one by one. Let's say that read write is also equal to 1, meaning that we are going to read from the memory. Then we will have 1 here, 0 out of the inverter, and then we will have 0 at the output of the AND gate over here, and this will result in zeros here and there, zeros here and there, zeros here and there, and therefore when we have this case, when we have reading, the content of memory will not change. It will remain the same, and that's what we want to have here. Because when we want to read, we don't want to modify the content of the memory. But then let's see what happens on the output side. When bit select is equal to 1, then here we will have 1 at the one input of the AND gate that we have here, and the second input comes from this SR latch. So therefore over here we will also have the Q as the data out, but let us see where that Q comes from. if we look at the output side of the cells that we have, we are connecting all of them to the inputs of OR gates. So the OR gates that you see here, they receive multiple inputs. So I can maybe draw one of them over here again. So there are multiple inputs to those OR gates, indeed 2 to the power of n, and each input is connected to the C output of one of the cells. So what you see here basically is the same as what we have here. Yeah, each input is connected to the C output of the cells, and just to simplify the representation, we just place an X between the line which is connected to the OR gate and the output of the C output of the cells. But on the other hand, we know that at any time instance, only one of the elements will be selected. One cell is selected, is activated indeed. So therefore, only all the outputs, C outputs of the other RAM cells will be equal to 0, and only from one we will receive the information. Let's say that C0 is selected, so RAM number 0 is selected, therefore C0 will appear here. And similarly for the others, we will have here not C and not C0, let's call it, and therefore since it is ORed with other not C's which are 0, over here we will have not C0 as well. And then with this SR latch, depending on the value of C0 and the not C0, Q will have some value which is basically the same as what we have for C0. If C0 is equal to 1, the latch will be set and therefore Q will be equal to 1. If C0 is equal to 0, then not C0 is equal to 1 and therefore latch will be reset and Q will be equal to 0. And therefore at the data out we will have C0. Okay, so basically the same information which is stored in the RAM cell that we are talking about. On the other hand, if we set read write to 0, let me just change this. So RAM select, bit select is still equal to 1, but read write this time is equal to 0. If read write is equal to 0, over here we will have 1 at the output of the inverter. From bit select we also have 1, therefore the output of the AND gate here will be equal to 1. We will have 1 here, 1 there, and then the data input, I can refer to it as D to make it simpler to show how it propagates in our circuit. So D will be here, and here we will have not D. After the AND gates, we'll have not D and D that you can see, and as a result, D and not D will be available at the input of the RAM cells. Depending on which RAM cell is selected, if let's say that this RAM cell is selected, select is equal to 1, then we will have 1 here, 1, 1, and D and not D will appear at the S and R input of the corresponding RAM cell. If D is equal to 1, then this will be set. If D is equal to 0, this will be reset. And as a result, the information will be stored in the selected RAM cell. So that's basically how the RAM bit slice works. And here you can see the block diagram in a more compact form as a single block. We have the data in input over here. We have the data out. Data is provided to the outside. The bit select is used in order to select this slice, and then we have the read write command as well. And on the right side here we have the address input. So that's what we have for the static RAM bit slice. Now here we have the RAM IC, okay, not bit slice, but we have the RAM IC. In order to have the RAM bit slice in the form of a proper IC, integrated circuit, RAM integrated circuit, we need to include some additional circuitry. First of all, we need to have a decoder. The decoder decodes the n address lines that we have to the power of n word select lines. Okay. So this is the symbol that we have over here. We have the symbol of the RAM IC, and here we have on the right side we have the internal structure. We have the 4 to 16 line decoder. As an example, we have n equal to 4, and then the output of this decoder gives us the minterms, which are connected to the word select of the bit slice, RAM bit slice. The data input is directly connected to the bit slice. Read write is also connected directly. Chip select is connected to the bit select input. And then on the data output side, we are using a 3-state buffer. This 3-state buffer is used in order to make us able to combine multiple number of these 2 to the power of n word by 1 bit RAM ICs to each other. You will see later how we connect these pieces of RAM into each other in order to expand our memory.